All right. So far we've been dealing with series of the form summation from k from 1 to infinity of ak, where ak is a constant. All right, we've studied these types of series, and we've established different tests to prove if such a series is convergent or divergent. An example would be, let's just look at very common series like 1 over k from 1 to infinity, and we know from using the integral test, this is divergent. It's a harmonic series, or a series of the form 1 over 2 to the power of k. Maybe we can throw in 3 here. This is maybe k from 0 to infinity. This is geometric series, and that converges because our r is just 1/2, less than 1, etc. Okay. Now consider a series of this form. Of the form k from 0 to infinity, and let's say we have ck, and then we have x to the power of k. Okay? X to the power of k. So we're introducing a variable x. So we have our ak in the previous series, and ak is a constant. Now we can think of this as our ak. But now our ak is no longer a constant. It has the variable x. All right? So for that reason, depending on the value of x, the function or the series might converge or might diverge depending on the value of x. And the series, if it converges, yields a different value depending on the value of x. Okay? Now, instead of just having x, I want to throw in something there. I'm going to delete this ak that I wrote here, and I'm going to make x look different. Instead of x, I'm going to write it as x minus some constant. Just call it a to the power of k. So we don't want just x alone. We don't want this. We want x minus a to the power of k. This makes it more general. All right. So we're going to give such a series a name. So such a series is called the power series, a power series. Oh, power series, not a power series. And we're going to spend our time studying when such a series converges and when it diverges. But let's introduce some terminologies. So in this power series, the ck, it's actually a little ck. Ck's are called the coefficients of the power series. A is called the center of the power series. So if a is 0, then we just have ck, x to the power of k, as I wrote before. And what else? So the set of values of x for which the series converges is called interval, the interval of convergence. So interval of convergence, the center, the coefficients. All right, something else we can think of is the radius of convergence. This is the distance from the center, the distance from the center of the series to the boundary of the interval of convergence. It's called the radius of convergence. Radius. And this is usually denoted with the letter R. Okay. So far, we have the coefficients, the center, the interval of convergence, and the radius of convergence. Okay, if you look at this, since this has an x in it, it's possible that it could be a function, and we don't know if it's a function or not, but we're going to begin, or we're going to maybe try to be thinking of this as a function. All right, maybe we can we think of this as a function since it just has x in it? So g of x is equal to summation of ck, k from 0 to infinity, and then x minus a to the power of k. Is it a function? Is it? All right, so that's one of the questions we're going to be answering. Okay. Now, well, the best way to learn in math is usually to do some examples. So let's look at some examples. We're going to look at examples where we're going to be looking for the interval of convergence and the radius of convergence. So let's look at some power series. So we have examples. The first one, let's look at the series k from 0 to infinity of x to the power of k over k factorial. All right? So think about this. What does this mean? Let's expand this. So this would be when k is 0, we have 1 over k factorial. That's 1 over 1. So we just have 1. When k is 2, when k is 1, we have x to the power of 1 over 1 factorial, so we just have x. When k is 2, we have x to the power of 2 over 2 factorial, so that's x squared over 2. When k is 3, we have x cubed over 3 factorial over 6, and so forth. So that's what we have. Now, this looks like a polynomial, but it's like an a polynomial with infinite number of terms. Is it a function? We don't know. But it looks like a function. So maybe we're going to start by treating it as a function. But before we do that, let's explore this more. So let's see, what is the radius or the center. Let's look at the center. The center, to do the center, we have to write, we don't have to, but let's just think about it this way. What about if we write 1 over k factorial x minus 0 to the power of k? Okay, so this looks more like what we have going starting out. So this is our ck, and this is x minus a to the power of k, right? So our center a is equal to 0. With this, we can easily write down the coefficients. The coefficient ck. Coefficient ck is 1 over k factorial. All right. Now let's talk about the interval of convergence. The interval of convergence. To do this, we have to harken back to the things we studied when we studied series, like regular series without x. Okay. So the center of the power series we just did is 0, and the coefficients are 1 over k factorial. So let's to go for the interval of convergence. I'm going to just say I of c. I just made that up. Let's use the ratio test, and I'll show you how. So we're going to say r is equal to the limit as k goes to infinity of our ak. Think about, what am I calling ak? Now we're going to treat the whole of this as a regular series. So the whole of this part is our ak. So remember that the ratio test is the limit as k goes to infinity of ak plus 1 over ak, right? But in this case, let's look for absolute convergence, right? Because absolute convergence is stronger than regular conditional convergence. Okay, so this will give us the limit as k goes to infinity. Our ak plus 1 is 1 over k plus 1 factorial. 1 over k plus, or let's do it this way. So ak plus 1, we're just going to go in here, and all the k's, we change it to k plus 1. So we get x to the power of k plus 1 over k plus 1 factorial. And then we're going to divide it by ak, which is like multiplying by the inverse of ak. So it's going to be k factorial over x to the power of k. All right, we learned a lot about factorials. So we know that we can start by rewriting this as x to the power of k times x over k plus 1 times k factorial times k factorial over x to the power of k. And this and that will cancel out. This and this will cancel out. And then we can factor out absolute value of x and then have k to the power of infinity. So why am I factoring out absolute value of x? Because the limit is in terms of k, so this x can just be treated as a factorial, as a constant. So I'm factoring out the absolute value of x since everything is in an absolute value. So with this done, I'll be left with 1 over k plus 1. So if I do this, this whole limit is absolute value of x times the limit, and that this limit is 0 as k goes to infinity. So we just have 0. What does this tell us? Okay. So this means that for all values of x, we have our r is 0. So remember, with the ratio test, when the r is 0, that means that the limit converges. Okay, so we can say, therefore, that means, the series converges. So the series converges. And most importantly, it doesn't depend on the value of x. X could be 1,000, x could be 100, x could be 1,000,000, x could be 0.5. But this limit is always going to go to 0. So it doesn't depend on the value of x. So we can say that the series converges for all values of x. All right. So we can now think of our interval of convergence. We can say the interval of convergence is thus for all values of x, so x between negative infinity and infinity. That's our interval of convergence. Since I've been writing things in red, I might as well write this one in red. style red. That's our interval of convergence. So this was, I should have done interval of convergence slash radius of convergence slash r, radius of convergence. Okay. So our r, radius of convergence, is now going to be, remember the definition of the radius of convergence, the distance from the center of the series to the boundary of the interval of convergence. All right, the interval of convergence is infinity, from infinity to infinity. So if the center is 0 and the boundary is all the way in infinity, so our radius of convergence, r, is just going to be infinity. Now let me make it red. Why not? Just for this problem, I'm going to write a bunch of things. But for the next problems, I'm going to act like I have only one color, just blue. All right. Let us review a little bit. So we have our series. We have this series, right? And then we have, we could find our center, because if we just rewrite this as 1 over k factorial x minus 0 times x minus 0 to the power of k, our center is easily decipherable. A is 0, which is our center, and our coefficients is 1 over k factorial. And to get the interval of convergence and the radius of convergence, we just use the ratio test. Remember, the ratio test says that if we find our r, which is the limit as k goes to infinity of a k plus 1 over ak, and if our r is between 0 and 1, 1 not included, the series converges. And if our r is 1, the test is inconclusive. And if our r is greater than 1, the series diverges. In this case, the r is 0, less than 1. So the series converges for all values of x. The interval of convergence, since it doesn't depend on x, for all values of x, the interval of convergence is x goes from negative infinity to infinity, and the radius of convergence is infinity. So let's try a second example, number 2. So how about that? K from 0 to infinity, negative 1 to the power of k, x minus 2 to the power of k over 4 to the power of k. All right, in this case, we have an alternating series, but it doesn't matter because we're always going for absolute convergence anyway, like we did in the other problem. So let's figure out what is our AK, our center. A center is equal to, why am I writing this in red now? I want blue, even though I went red the last time. Now I'm just gonna go blue, do everything with blue. Our A, the center, A is equal to 2. Our coefficients, CK, is equal to negative 1 to the power of k over 4 to the power of k. Okay. All right. Now let's look for the interval of convergence and the radius of convergence. So interval slash radius of convergence. We're going to apply the root test. All right, to apply the root test, rho is limit as k goes to infinity of the root of our AK. Our AK in this case is just this whole thing. All right, so negative 1 to the power of k. Remember, we're going for absolute convergence, so we have to absolute this whole thing. X minus 2 to the power of k over 4 to the power of k. So we can actually just do this. Bring out all our k's, put it over here since everything is in terms of k, right? If you now raise everything to the power of k, the k's will go back in. All right. Well, let's how about we go patiently, do this, do that, and then we have limit as rho goes to infinity. Oh, kth root, not square root. I always make that mistake. All right, kth root of absolute value of -1 to the power of k, absolute value of x minus 2 to the power of k, absolute value of 4 to the power of k. All right, so this is limit as rho goes to infinity. What am I doing, rho going to infinity? What is wrong with me? K goes to infinity, now rho goes to infinity. I should learn how not to rush things. All right, so we have the kth root of 1 to the power of k, of x minus 2 to the power of k, or absolute value of x minus 2 to the power of k, and then 4 to the power of k. If you find the kth root of all these things, this becomes the limit as rho goes to infinity of absolute value of x minus 2 over 4. All right. Now, we want this to go to, for convergence, we want this value to be less than 1. All right. So I'm going to write that. So for convergence, we want, or we need, but in this case we want, because we want this to be less than 1. This is 4, not to be less than 1, which implies that we want x minus 2 x minus 2 to be less than 4. This means that we want x minus 2 to be between, let's say we want x minus 2 to be between -4 and 4, right? So we want, and what does that mean? We want x minus 2, if you add 2 to both sides, so that you get rid of the 2 in the center, you have x is between 6 and -2. Okay. All right. So what do we have? Okay. So now we have that. Let's see what we have. That's our interval of convergence. So interval of convergence contains, and why am I using this word? You see why. It contains from -2, oh, not red, blue, -2 to 6. Now, what happens at the end point, right? Because we want to get as large an interval as we can. So how about what happens at 2 and 6? Can we get it to be, instead of the open interval, can we include -2 and 6 so that we get this? All right. So, well, let's see. How about we check at -2 and -6? That's easy to do. At -2, our series become the power series. If we plug in -2 to the power series, to this power series, let's cut and paste. We can cut and paste. Cut and paste, cut and paste. All right, so we cut it, put it right here. Now, let's plug in -2 for x. Oh, if you plug in -2 for x, what do you get? You get -4. You get -4 to the power of k. Yeah, so you get -1 to the power of k times -4 to the power of k over 4 to the power of k. So this will give you summation. -1 times -4 is just 4, so this is 4 to the power of k. And check this out. This is equal to 1 to the power of k. 1 to the power of k is always going to be 1, all right? So our k start from 0 to infinity and blah, blah, blah. We got to put that, all right? So k from 0 to infinity of 1. Think about it. You're adding 1 from 0 to infinity. 1 plus 1 plus 1 plus 1, infinite number of times. This diverges. Oh, all right, this diverges. So at 2, it diverges. At 2, the series diverges, the power series diverges. How about at 6? What happens at 6? So remember what we're doing? Same thing here. We're just taking this and we're plugging 6 in there. So at 6, what do we get? We get summation k from 0 to infinity, -1 to the power of k. Plug in 6 there, you get 4 to the power of k over 4 to the power of k. These cancel out nicely. Cancel, cancel. So we just have k from 0 to infinity, -1 to the power of k. So think about this. This is the same thing as 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so forth. This diverges because it doesn't add up to one thing. Think about it. From here to here, we get 0, but if you add 1 here, it becomes 1, then it becomes 0. So it oscillates between 0 and 1. It diverges, happily diverges. It diverges. All right, so at the endpoints, there is no convergence. That's not always the case. So it's not this. So we just have to go with what we have with this. And we can't say, instead of saying contains, we can actually say is, all right? Because we've proven that at the end point, it diverges, all right? So our interval of convergence, is -2 to 6. All right, now we're left with the radius of convergence. That's quite easy to do. What is the center? Our center is 2. Now let's look at this interval of convergence. If you look at this interval of convergence, you can see, if we go like this, you have 2, 3, 4, 5, 6. And they have 1, 2, 3. -1. No. You have 1, 0, -1, and -2. 2 is the center. These are the endpoints. What is the radius of radius? The radius is the distance from the center to here. and the distance from the center to here. The two distances have to be the same thing. So the radius of convergence here R is equal to 4. Okay. All right, so what else should we do? What can we do? What would you do? Okay, so let's do one more. Let's do one more. How about number 3? We have that k from 1 to infinity of k factorial of x to the power of k, right? Our a, center a is 0. Our ck is k factorial. So interval / radius of convergence, go with ratio test. I'll have limit as k goes to infinity of ak plus 1 over ak is equal to limit as k goes to infinity of k plus 1 factorial over x to the power of k plus 1 over k factorial over x to the power of k plus k. All right. So this is the limit as k goes to infinity of, let's see, k plus 1 factorial is k plus 1 times k factorial, x to the power of k times x over k factorial over x to the power of k. Now cancel. Now what are we left with? We're left with the limit as k goes to infinity of absolute value of x times absolute value of k plus 1. So, which is the same thing as absolute value of x times limit as k goes to infinity of k plus 1. This doesn't depend on x. This is going to go to infinity irregardless of the value of x, right? If x is unless x is 0, right? If x is not 0, it's always going to go to infinity. What did I just do? My stuff is acting up. I'm trying to circle this and it's just messing up. All right, well, I don't have to do that. So let's go back to blue. Whoa. Whoa, my stuff is messing up. Guys, you know what? Maybe we should end here since I can't write anymore. This is terrible. This is horrible. Can I do anything? Can't write. Maybe it's out of battery. I don't know. Okay, we're going to end here. But this limit, this particular limit is equal to infinity. Since it's equal to infinity, that means our radius of convergence is 0, right? Oh, sorry, our interval of convergence is 0 because this diverges for any value of x, right? It doesn't converge. It only converges when x is 0 at the center. So it diverges for any value of x. And then what else can we say? What about our radius of convergence? Right? Our interval of convergence is 0. And then our radius of convergence is also 0. I'm trying my best to get this to work. And it's just messing with me. Okay, let's see. All right. Let's see if this works now. No, really? Wow, that is so dangerous. Oh, okay. I got it. All right, so this limit goes to infinity, right? Thus, series diverges for every value of x. All right, let's go back to the previous example. So here, this is the interval for which the series converges, this interval, and the radius of convergence is 4. However, over here, it diverges for every value of x, possibly not as x is equal to 0, since the center is equal to 0. So let's do this. If this is the center, this is the only place where it converges. Every other place it diverges, right? So our interval of convergence is just this point, the center. Because the center is 0, that's the only point where it doesn't diverge. If you plug in 0 for x, then you get 0. It converges to 0. And the radius of convergence my handwriting is messing up, it's screaming, is 0. Okay, I think we should stop here.